So today we're going to talk about section 7.2. On frequency and a probability distribution. Okay, so we're going to start with an example to talk about these ideas. Let's say there are two car dealerships. And they both give sales data. And this is how they give the data. They give the number of weeks where they have weekly car sales of, say, 5 cars, 6 cars, 7 cars, 8 cars, 9 cars, 10 cars, and 11 cars. And then they tell this is the number of weeks sales are equal to the number at left. This may seem strange, but this is perhaps how they do it. And we have two dealerships, so let's say dealership A will be right here. So the number of weeks they sold 5 cars was 2 weeks. The number of weeks they sold 6 cars was 2 weeks. The number of weeks they sold 7 was 13. Number of weeks they sold 8 was 20. Number of weeks they sold 9 was 10. Number of weeks they sold 10 was 4. And the number of weeks they sold 11 cars was 1. So that is the information that dealership A provided for us. Okay. So how many of the 52 weeks in a year did they sell 7 cars? The answer is 13. And if you sum these numbers, let's see, what do we get? 5, 6, 7. Yes, we get 52. 52 weeks. Okay. Now, dealership B gives us its weekly sales data as well. So we get 20, 0, 0, 10, 12, 50, and 12. Oh, okay. Something is weird. Something is different here. The number of weeks they sold 10 cars was 50, right? But there's only 50 weeks in a year. If we add these up, we get 104. And then we discovered, oh, dealership B has given us 2 years of data, and dealership A has given us 1 year of data. Well, suppose now that you are thinking about purchasing one of these dealerships. How do you decide how to do that? Well, the data is very different. One is 1 year data, one is 2 year data, so we need to do something to try to compare apples to apples, right? We're comparing two different things now. Obviously, dealership B looks better because look at that. Dealership A sold 10 cars only 4 times, but dealership B sold 10 cars 50 times. Like, that's insane. Right? But, so we need to figure out a way to compare these reasonably. And the way we will do this is called looking at the relative frequency distribution of each dealership. Okay, so I want the relative frequency for A and the relative frequency for B. So, on 2 of the 52 weeks, they sold 5 cars. So the relative frequency of the number of weeks they sold 5 cars is going to be 2 divided by 52. This is about 0.04. And so every number in this column is going to be the number in the column for A divided by 52, because we want the relative frequency of these occurrences. So we get 0.04, 0.04, and these are approximates, of course, 0.25. That's an exact one. 0.38, 0.19, 0.08, and 0.02. And if we add these together, we should get 1. Right? So these are the relative frequency. So now we can say 38% of the weeks they sell 8 cars. And that's what this is saying. Or 8% of the weeks they sell 10 cars in a given week. Does this, how I made this table, make sense? Do you see where I got these numbers? Is this fine? Yeah. Okay, one person agrees that this is fine. Okay, perhaps even 7. Great. All right. That's enough to move to the next table. So now, for these numbers, I'm not dividing by 52. I'm dividing by 104, the number of weeks in 2 years. So here we get 0.19, 0, 0, 0.10, 0.12, 0.48, 0.12. And these, of course, will sum to be 1 as well. Now we can compare these dealers a little bit better. Now we can see, okay, well, 38% of the time dealership A sells 8 cars, but 48% of the time dealership B sells 10 cars, right? So now it's a little bit more easy to compare these two dealerships because we have the relative frequencies. Okay, that's what we mean by a relative frequency distribution. Okay, now we could draw histograms with this data for the two dealerships to compare what's going on. So to compare with a picture, we use the relative distribution in order to get both of these on the same scale. So dealership A, 5, 6, 7, 8, 9, 10, 11 would look something like this. Okay, I'll draw the scale in a second here. Just trying to draw a picture similar to the one I've got in my notes. Okay, and this would be 0.40, this would be 0.20, this would be 0. So that's what dealership A would look like in terms of a histogram. And dealership B would have a different histogram. 5, 6, 7, 8, 9, 10, 11. Here we have something like this. Now we have no box at 6 and 7. 8 is 10%. 9 is 12%, so a little higher. 10 is 50-something, 48%, almost 50%. And 11 is 12%. Okay. Now, when we look at these histograms, they're both on the same scale, and it allows us to compare them a little bit better. Now, of course, we're not in this section going to learn basically what we want to know is how many cars did each sell and which one sold more cars, right? Now, of course, they might have different prices, and then we'd have to figure that out. But this is just the relative frequency distribution. Okay. So when we have data like this, we don't really know how often the outcomes occur, right? If you look at this and you say, okay, car dealership B seems to be selling way more cars than car dealership A, and you buy car dealership B, that doesn't mean that next year car dealership B is going to sell more than car dealership A, right? Because these are just random occurrences in the world that we can't really control. But for certain experiments like coin flipping and die rolling, we actually know how often things occur. We know their distributions. Okay? So with theoretical experiments, we know the probability distributions. We're not just guessing them from data. Okay, so here is an example of how we could deal with this. Let us find the probability distribution for the number of heads found when tossing a coin 5 times. Then draw a histogram. So we have the tools now to figure out this problem right now, because we learned all about counting, we learned about sets, we learned about sample spaces, experiments, and all this, and so we have the tools now to do a problem like this. So the total number of outcomes in the sample space, we're tossing a coin five times. There's 2 possible outcomes, so this is going to be 2 to the 5th, which is 32. There's 32 total outcomes. And so now we want to know the number of outcomes. Well, let's make a table here. Okay. Outcome. The possible outcomes are 0 heads, 1 head, 2 heads, 3 heads, 4 heads, and 5 heads. Okay, and then we want to count number of outcomes which have all of these. To find the number of outcomes with 0 heads, this is choosing 0 from 5, combination of 5, 0, which is 1. This is the next one, 1 head, is combination of 5, 1, which is 5. 2 heads is combination 5, 2, which is 10. 3 heads is combination 5, 3, which is 10. 4 heads is combination 5, 4, which is 5. And 5 heads is combination 5, 5, which is 1. So those are the total number of outcomes that have each of those number of head possibilities. And now we're ready to write the probability distribution. The number of 0 head outcomes is 1, and there's a total of 32 outcomes. So this is 1 over 32. The number of 1 head outcomes is 5 out of the total 32, so this is 5 out of 32. The number of 2 head outcomes is 10, so this is 10 out of 32. Again with 10 out of 32 for the next. 4 heads, we get 5 out of 32. And 5 heads, we get 1 out of 32. And if you note, you add all these numbers, you get 1. Right? If you have all of the possibilities accounted for, and you add all of the probabilities associated to them, you should get 1, because something must happen. Do you see how I made this probability distribution table? Perhaps you see, but don't quite care. Okay. Sorry about that. Okay, and then we were supposed to draw a histogram, right? So we still have that to do. So I'll draw my histogram. You have 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads. This is going to be 0.1, 0.2, 0.3. Okay, 0 heads is 1 out of 32, which is a pretty small possibility. 1 head is 5 out of 32. Okay, so that's going to be, let's see, about 15%. 2 heads is 10 out of 32. That's about a little less than 30%. Same with 3 heads. There we go. Okay. So there's our histogram that shows the probability distribution for the number of heads you get when you toss a coin 5 times. Now we could easily answer questions like, what's the probability of getting at least 3 heads? Oh, okay, well, at least 3 heads, we would add the height of this bar, and this bar. So probability of at least 3 heads. We would get 10 32 plus 5 32 plus 1 32, and that is going to be 16 out of 32, which is exactly 1/2. So half the time we'll get at least 3 heads. And then, of course, the complement to at least 3 heads is at least 3 tails, which has the same probability. Okay. So now we're going to add some notation, which is a little bit weird. Okay, I'm gonna admit this is kind of weird notation. It is the way it is because of historical reasons, and using it will allow us to sometimes do some more complicated things with it. So that's why we use it. So this is the idea of a random variable. If an experiment has numerical outcomes, we can represent it by a letter, usually capital X, called a random variable. So a random variable is a letter that represents the possible outcome of an experiment where we have numerical outcomes. Now, I drew this fancy capital X with bars on the top and the bottom, not because you have to draw a fancy X, but because I want to make sure my uppercase X's and my lowercase X's look different enough for you guys. So that's just an uppercase X. That's all that is. If your handwriting is good enough that an uppercase X and a lowercase X never look the same, then you don't need to be careful at all. I am not in that boat, though. Okay, so let's recast the last example in this language of random variables. We'll let X be equal to the number of heads found on 5 tosses. And now we can make sense of statements like the probability that the random variable X is equal to 0. This means the probability that we will see 0 heads in 5 tosses. We already calculated that. That was 1 out of 32. Or we could say, what's the probability that X is equal to 3? The probability that we see exactly 3 heads in 5 tosses. We calculated that. That was 10 over 32. Now we could say, what is the probability that X is bigger than or equal to 3? This is saying, what's the probability that the random variable is equal to 3, 4, or 5? Oh, well, we just figured that out. That was equal to 1/2. Okay? So you can see how maybe this notation can make things a little bit faster. I just say X greater than or equal to 3 instead of writing a big sentence down. And so now we can make a table. Sometimes the way you're going to see these tables is like this. Your numerical outcome is K, and then on this part of the table you'll have the probability that the random variable is equal to K. And so for this experiment, I'm just repeating this table, but in the new language. Oops, I forgot 2. Yeah, that's a problem. And we all like 2. Okay, so there's a table that displays the possible values of a random variable. We'll do another example with random variables that is a little, perhaps, I'm not going to say it's perhaps a little more interesting. It is more interesting, but little is probably the amount that it is more interesting by. Not a lot. So don't get too excited. I can tell your enthusiasm is fully curbed, so we're ready for this next one. Okay. Let X be the sum of a roll of 2 dice. See, I told you it's not that much more interesting. And let's find the probability distribution of the random variable X. So what we want to get is we want to get a table like this. And the possible sums for a roll of 2 dice are, of course, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And now what we want to do is we want to put a probability, of course, a number between 0 and 1 on the right-hand side for each of those numbers. And so we have to figure out what those numbers are. I think the best way to do this is to draw a table of the possible outcomes, as we've done before. So the vertical is the number you get on the first toss, and the horizontal is the number you get on the second. And then, of course, we can fill this out. 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. All right, so there's all the possibilities there. Of course, as we know, 36 possible. So the probabilities are always going to be some number over 36. We just have to count the occurrences of each of the numbers. We have only 1, 2. And so this is going to be 1 out of 36. All right, the number of ways we can get 3, it looks like there's 2 ways we can get 3. So this would be 2 out of 36. 4, there's 3 ways, 3 out of 36. 5, there's 4 ways, 4 out of 36. 6, there's 5 ways. 7, there's a total of 6 ways to get a 7. And then the numbers go down from there. There are only 4 ways to get a 9. There's 3 ways to get a 10. 2 ways to get an 11, and 1 way to get a 12. So there is our probability distribution of that random variable. The probability that X is equal to 6 is 5 out of 36, a little less than 1/6. The probability that X is equal to 7 is 6 out of 36, exactly 1/6. Okay. Now, this may seem like a pointless question to ask, but you could perhaps see a little bit of the power of the way this works. Now we could say, what is the probability distribution of X squared? We want to know what's the probability distribution for the square of the sum of 2 dice. Okay, well this is... Okay, so here we have K, and then we have probability of X squared equaling K. Okay, 4 is the smallest possible square we can get, and that happens when we get 2. But we can't get the number 5, 6, 7, or 8. So this random variable can't be equal to 5, 6, 7, or 8. So that would be 0. But of course it can be equal to 9, and it is equal to 9 with probability 2 over 36, because that's what happens when we get a 3 for the roll. And the study of mathematical probability, right, if you were to decide, hey, I want to become an actuary, which is a great career if you like math and staring at a computer screen, you have to take a test in probability theory. And you will become conversant in this language of random variables. You might multiply a random variable x with a random variable y and be asked what's the value that you expect to achieve with this and things like that. So if this would be interesting to you, that's an example of what probability theory does, right? We start to do algebra with these sorts of things and make conclusions and predictions about the world based on that. Okay, so let me write down the homework for this section. This is section 7.2. Numbers 2, 10, 14, 16, 18, 22, and 28. Okay, so on Friday, we will have a quiz. Let's say the quiz on Friday will be from possibly the last part of chapter 6. So that would be 6.6, Bayes' theorem, or 7.1 and 7.2. 7.1 was charts, and 7.2 is today. Okay, so those are the possible things that might show up on the quiz on Friday.